SAP 2000 can automate the application of wind loads using several different techniques. In this tutorial, we will show how wind load can be applied using either rigid floor diaphragms or by using area objects such as walls. We will show both techniques. For this example, our model will be a 3-story tall building, 3 bays by 2 bays, with a smaller top story. Each story is 12 feet tall, and the bays are 24 feet wide. We will be working in pound-feet units. Automated wind loads are generated using the load patterns command. We start by defining a wind pattern with a type of wind. The automated loads are specified using the auto lateral load drop-down list. Here we have a number of choices for the code, and many work in a similar way, such as the NBCC and the ASNZS. But we are going to use the ASCE 7-10 code for this model. Once we have selected the code and added it to our load patterns, we click the Modify Lateral Load Pattern button. The wind load pattern form is where we specify the parameters required by SAP 2000 to generate the wind load. Note that we have 2 options. Loads may be determined based on exposure from extents of rigid diaphragms or exposure from frame and area objects. Using the extents of the rigid diaphragms to define the wind loads is a very powerful option, and we will examine this at length. But first, we will explore how the exposure from frame and area objects works, which is a bit less automated than the rigid diaphragm option. When selecting this option, we have the choice of using area objects, or frame objects, or both. Note that for area objects, we will need to assign the coefficients C sub p directly to the objects. C sub p are wind pressure coefficients that are used in equations along with gust factors and velocity pressures to determine design wind pressures. With this option, the input required on this form is primarily concerned with the site factors, such as wind speed, exposure type, and gust factors. If we include frame objects, we can also set the solid to gross area ratio. But our model is a closed building, so we will not include frame objects. Wind loads typically vary over the height of the structure, and the program will automatically calculate the variations in wind pressure due to height. The height used may be program determined, which is what we will use, but the user may specify their own values if desired, which may be useful for structures that are partially shielded from the wind. Now let's look at how we assign the C sub p coefficients to the objects. In this case, the load pattern we defined was for wind blowing in the positive y direction. Because we are using the exposure from objects option, we will start by applying the C sub p coefficients to area objects. The walls on this side will be on the windward side when the wind is blowing in the y direction. We will switch on the local axes and switch off the extrusions. Note that the local 3 axes, the blue ones, are going in the negative y direction. This is important because the wind pressures are applied to the objects in the local 3 axes directions. Note that although we are only showing structural walls in our model and will only be applying wind loads to these walls, in reality, the building is completely enclosed and wind loads should typically be applied to the exterior non-structural walls as well. We will select the three area objects on the windward side. And go to the Assign, Area Loads, Wind Pressure Coefficients command. Selecting the wind load pattern. Remember that the area objects selected were on the windward side, and because they are on the windward side, the program will automatically vary the pressure based on the height of the objects. For the windward side, we will specify a C sub P of minus 0.8 negatives so that the wind pressures will be applied normal to the area object in the opposite direction of the three axes, which results in wind pressure being applied in the positive Y direction. Now we will spin the model around to the other side and select the three area objects on the leeward side. The wind pressure will be constant on this side. Again, we go to the Wind Pressure Coefficients command. But this time, we will select the other option so that the wind will be constant over the height. We will enter a C sub P value of minus 0.5. And now we have a C sub P of 0.8 applied to the windward side and a C sub P of 0.5 applied to the leeward side. If we right-click on an area object and go to the Loads tab, we see that the component is 0.5 in the positive Y direction, as desired. Although our model is a closed building, to apply wind to frames in an open structure, we select a frame and go to the Assign, Frame Loads, Open Structure Wind Parameters command. Here we can specify whether the object is loaded by wind. The default is yes. Whether the surface should be increased due to ice, and also specify the force coefficient C sub F, which is used to calculate the force on the member. However, in this model, we are not going to load any frame objects with wind, only the area objects. We can now run the analysis. With the analysis complete, we will switch to a plan view, go to the Display Deform Shape command, and select the wind case. However, remember that we have defined only one wind load case, wind in the Y direction. There is no wind in the X direction, or in this case, any torsion. Yet codes often require the application of wind in multiple directions, and to include the effects of torsion. And this is where the rigid diaphragm option is very powerful, which we will now illustrate. Rather than having to manually define many different load patterns to account for the different permutations of wind loads required by codes, and then assign coefficients to objects throughout the model, SAP 2000 offers an automated procedure that simplifies the work. In order to use the automated wind load option, rigid diaphragms must be defined. Using the same model, we go to the Define Joint Constraints command. Here we will define a rigid diaphragm for each floor, a total of 3. The rigid diaphragm should be constrained about the z-axis. We will not use the semi-rigid option, as this is typically more appropriate for tall buildings with many stories, where the wind load at any story is small relative to the forces being transferred through the diaphragms. We will define 2 more. For a total of 3 rigid diaphragms. Switching to a plan view at the first floor, we will select all of the joint objects and assign diaphragm 1. Moving up to the second floor, we will assign diaphragm 2. Lastly, at the top floor, we will assign diaphragm 3. Now we will define the wind load pattern. This time naming the pattern wind. We will again select the ASCE 7-10 for the auto lateral load pattern. Clicking the Modify Lateral Load Pattern button, we will this time select the exposure from extents of rigid diaphragms. The wind direction angle will be 0, which in this case means the dominant directions of the wind will be in the global X and Y directions. With this option, the C sub P coefficients are specified on this form rather than on objects, and again will be 0.8 for the windward and 0.5 for the leeward side. The E ratios are used to determine the torsion effects, and these are the ones set for the ASCE code. The real power of this technique is the fact that it will generate multiple cases. The ASCE code has 4 defined cases, and we will ask for all 4. This will generate a total of 12 different load patterns. This takes care of applying the load in different directions and with eccentricities to satisfy code requirements. The vertical area used to generate the wind loads is based on the dimensions of the rigid diaphragms and the story heights. If we click the Modify Show Exposure Widths button, we can verify the dimensions generated by the program. Here we see the width the program will use for wind in the X direction and the widths for the Y direction. Note the smaller dimension for the top floor. The tributary story heights used are listed here. If we select User Defined, the spreadsheet becomes unlocked and we can edit values, such as increase height for a parapet. Note that the loads are applied at the geometric centers of the diaphragms. And on this form, again, we will use the program-determined exposure heights and we'll leave the wind coefficients as shown. If we exit and then return to the load patterns form, we see that there are now 12 wind patterns that have been created for the 4 code load cases. If we look at the first pattern, we see that it is being applied at 0 degrees, which is in the x direction, and is part of case 1, which has no eccentricity. If we look at the second pattern, we see that it is the same, except that it is applied at 90 degrees or in the y direction. Now we will shut off the extrusion and run the analysis. Note that 12 load cases have been generated for wind. We will shut off the modal case as it is not needed. With the analysis complete, we can step through the deformed shapes for all of the wind cases, 1 through 12. This includes loads in both directions, as well as torsion loads. The applied wind loads may be verified by using the display show element load assigns joint command. Here we can see the loads applied at the center of each rigid diaphragm, which includes both windward and leeward forces along with torsional moments. If we look at results in tabular form, for example, base reactions, we see the results have been generated for all 12 load cases. If we generate the design load combinations, which creates a great many combos due to all of the wind cases. When we look at a few, note that the wind is applied in the plus and minus directions. This concludes this tutorial on automated wind loads in